In solids, the particles are in a fixed framework. They're held close together and vibrate. In liquids, the particles are still in contact, but this time they're free to move around. The particles in a gas are far apart. They move quickly and randomly in any direction. A block of ice takes the shape of its mould. As it melts, it changes. The water spreads out and fills up the container. All liquids behave this way. They flow and find their own level. Spread out even more, filling any space available. The way solids, liquids and gases behave gives us clues about how their particles are arranged.
To understand what's happening, you need to know exactly what's going on when something dissolves. You need to look at it really closely. Imagine you had an eye more powerful than the most powerful microscope. What might you see when sugar dissolves in water? The water itself is made up of many tiny particles, all moving around randomly inside the container. The sugar is made up of bundles of sugar particles called crystals. When the sugar dissolves in the water, the bundles of particles which make up the crystals break up. They become completely mixed with the particles of water. All the particles move around freely and the whole solution behaves as a liquid, so you can't see the sugar. The sugar particles move around in the gaps between the water particles. There's room for them to slip in between. This means the volume of the solution does not increase that much when sugar is added. So you can add more than you think before the glass overflows.
What I don't understand is why doesn't the salt dissolve? I mean, there's loads of water around.
Well, I tell you what, let's gather up some and we'll have an experiment.
Okay.
A strong salt solution is being prepared by Diane, who works here. But soon the salt stops dissolving.
So much salt has dissolved that it can't dissolve anymore.
Exactly. That's what we call saturation.
Right.
If I was to take this solution and pour it into this beaker right here, and we was to leave it in the sun for a while, it would eventually evaporate and we would have crystals left.
Starting with a saturated salt solution means as soon as any water evaporates, the water that's left can't keep all the salt dissolved. So, salt crystals appear. Hi George, I've collected my rock salt sample for analysis, so what do I need to do?
Well done, Trish. And put the rock salt nicely on the weighing paper.
Lovely jubbly. Take 100 grams of fresh crushed rock salt. Add water and mix well for 2.5 hours. The salt dissolves, but of course the clay does not. Pour the mixture through a filter. The clear salt solution passes straight through into the flask. But the brown clay particles are too big to get through the filter paper. Heat the salt solution. The water evaporates, but but the salt is left behind. By subtracting the weight of an identical empty beaker from the weight of my salty one, I can calculate I have 94.8 grams of salt. So George, 94.8 grams of the original 100 grams mixture is pure salt.
Yes, that's right, sis.
So what we have here is nearly 95% salt.
Yes, that's right.
You can find lots of examples of rust.
Rust is the product of a chemical reaction. The iron reacts with the oxygen in the air or in the seawater. It's a form of oxidation. It also needs moisture, and there's no shortage of that on a ship, and it leads to corrosion like this.